Remember that in section 27 we're talking about these mathematical objects known as a permutation. A permutation informally can be thought of as a rearrangement of a set of objects, but technically it's actually a function, which means formally, if we wanted to say what kind of object, mathematically, what kind of object is a permutation, it is just like a relation, it's an ordered pair set. There are a set of ordered pairs. Like this right, oh, you can't see what my little pen looks like. Hold on. Try this guy. There's my pencil. Can you see him now?
No, we're frozen.
You're frozen. Dadgummit.
We're on the crossing out of cycle notation. Do the inverse permutation.
Okay. So this right here is one way of representing a permutation, and it is doing it as a set of ordered pairs. And what that means is, again, for a permutation to be a permutation is you're taking one set of objects and mapping it onto itself. So the inputs and the outputs are from the same set, and every, of course, input occurs once, every output occurs once. So that way you're completely onto the set itself. You couldn't have two different points mapped to from the same point, and you couldn't map two different points to the same point or the same element of the set. And when we write it as an ordered pair, this just means that 1 goes to 2, 2 goes to 4, 3 goes to 1, 4 goes to 3, and 5 goes to 5. We can draw it with a table. We can write it as an ordered pair. I taught you that you can do it as an array notation, where you just put the first row as the numbers 1 through n. The second row is what each one of them map to. And then we also learned later on that we can use something called cycle notation. You can go back and review how to do compositions and permutations. We'll talk a little bit more about them in a second, but just remember that inverse inverse permutations just map them backwards. Whatever mapped, point A to point B, the inverse would map point B to point A. But cycle notation is a third way of writing down a permutation. You have ordered pairs, you have the array notation, but then you have these cycles. So this array right here tells you that you're going to rearrange the objects 1, 2, 3, 4, 5 into 2, 4, 1, 3, 5. But we can also write that same permutation using this cycle notation. And the cycle notation is you start with one element and you see where it takes you. Right? 1 then goes to 2. And then you ask, where does that output take me? 2 then goes to 4. And then you go over here, and 4 then goes to 3. And then 3 then goes back to 1. So this right here tells you everything about the permutation that this one tells you. I know, for example, if I just asked off the top of your head, where does 4 go? You can tell from looking at this that 4 goes to 3. 4 maps to 3. 4 is moved to the third position because 3 comes over. And you just move left to right on the cycle. And when you get to 3, 3 starts over, right? So 3 goes back to 1, 1 goes to 2, 2 goes to 4, 4 goes to 3, 3 goes to 1, and so on. That's why it's a cycle. Okay. This right here, we were able to show that if I give you an array, you can always turn it into a cycle. We walked through how to do that. If I gave you a cycle notation, you can turn it into an array pretty easily. And the last thing we were going to wrap up with is this idea of transpositions. Now, what makes something a transposition? A transposition essentially just has one pair in your cycle list. 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. In this case, 5 goes to 9, and 9 goes back to 5. And then 6, 7, and 8, they all stay where they are. So a transposition is exactly what it sounds like. You're just going to transpose two elements, flip them. And instead of writing tau this long way right here, or writing tau this way, I'm going to write tau in shorthand and just say the transposition 5, 9. So take a list of objects and just switch the fifth and the ninth, that's a transposition. It's a very simple permutation, but my claim here, that the last thing that I wrote, is that every permutation can be written as a series, a composition of transpositions. And let me show you by example that that's the case. And with a single example, you'll be able to see how you can write these down for any given problem. I want to start with pi is 1, 2, 3, 4, 5. That is a cycle notation. It says 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes then back to 1. Now what I'm claiming is that I can reorder a set of objects using this. You don't necessarily have to write this, but think about what that actually means as an array. 1 goes to 2, 2 goes to 3, 3 goes to 4, 4 goes to 5, and 5 goes back to 1. This is the permutation we're talking about. My claim is that I can get from here to here through a sequence of flips, just transposing 2 at a time. Okay? So I'm going to write as a composition of transpositions. All right, now let's refresh our memory real quick. I want to back up for a second. Remember whenever we were transposing, when we were composing up here, way up here, all right. We had pi and sigma in example last time, and I said find the composition pi composed with sigma. That means pi of sigma of every element in there. So to figure out what this map does, like for example where it takes 1, what you do is you first plug it into sigma. You plug it in from right to left, see where it takes you in sigma, and then plug it into pi and see where it takes you with pi. So like the element 1 here, I want to know what goes right here. Well, I say, okay, in sigma, where does 1 go? 1 goes to 5. So 1 goes to 5. And then in pi, 5 goes to 5. So that means 1 goes to 5. 1 goes to 5. That composition is the thing that goes right to left. We just do them one at a time. Okay, so here's my claim about transpositions. I claim this pi right here is the same thing as 1, 5 composed with 1, 4 composed with 1, 3 composed with 1, 2. Now again, remember, the order in which this occurs is from left to right. So what I'm really saying is that if you flip 1 and 2, and then you flip 1 and 3 in the result of that, and you flip 2 and 3, and you flip the third and fourth, and then you flip the fourth and fifth, in that order, you will get this same permutation right here. Let's check. And here's how you check. What you do is you start with the number 1 and see where it's supposed to go. Now, it should go to 2 when it's all said and done. Right? That's what this says over here, is that 1 should go to 2. That's what this says right here. 1 should go to 2. But if I write pi as a series or composition of these transpositions, let's do these transpositions in this order. So, ignore for a second all of this and just think of 1 to 2. That's 1, 2, 3, 4. This first transposition here says take 1 to 2 and 2 to 1. So where does 1 go in this cycle or in this transposition. Goes to 2. Okay? Now, let's try this transposition. By the way, remember that a transposition is really just a shorthand for this notation right here. So if I have a 1, 3, that means 1 and 3 switch, but what does everything else do? Stays the same. Right? This 1, 3 right here means that if you had a 1, it would go to 3. If you had a 3, it goes to 1. But everything else stays exactly where it is. So 2, by this transposition, by this permutation right here, still goes to 2. Right, because it's not a 1 or a 3. All right, and then 1 and 4. If you switch the 1 and 4 place, what happens to the 2? Stays. And then on the 4th one, if you switch the 1 in the 5 place, but the 2 stays there. So notice, what did 1 do? 1 went to 2. So that checks. What does 2 do? Okay, well, let's again do it from right to left. This transposition says 2 goes where? Goes back to 1. And this transposition here says 1 goes to 3. And now this transposition says 3 goes to, since it's not 1 or 4, it stays where it is. And this 1, 1 and 5 stays 3. So 2 went to 3. That checks. Okay, let's see what 3 maps to. Okay, so I'm going to use the first transposition on the right. 1 goes to 2, 2 goes to 1, so where does 3 go by map 1? Stays where it is. And then on this one, 3 goes to 1. By this one, 4. And then by this one, 4 goes to 4. So notice 3 went to 4 like it was supposed to. All right. Check. And then 4. 4 goes to 4. Maps to 4. Maps to 1, which then maps to 5. And then 5 maps to 5, to 5, to 5, to 1. Check. So, what you should be able to see here is that if you want to create a cycle, what you can do is simply write your transpositions as, like, here's what I'm thinking in my head when I see this. If I have a cycle that looks like this, then I start by writing that transposition right? Composed with, and now do that transposition. Composed with, and then do 1, 2, 3. Do you see where I'm getting it? You just keep going until you get the whole cycle done. That works with even longer cycles. You can turn cycles into transpositions by taking a transposition of the last composed with the transposition of the first with the next to last, first with the third to last, and so on. Here, let me do another example so you can kind of see that pattern again. Let's try it one more time. Let's let pi be a different permutation. And I'm going to write it in cycle notation. And I'm going to make one up off the top of my head. Let's do 4. No, I'll start with 1. I always like to start with 1. 1, 4, 8, 9. Let's do 3, comma 10, comma 7. Let's do 11. And then we'll do, what am I missing? A 2, a 5, and a 6. I'm up to 11 that way. Okay. So that's a permutation. 1 goes to 4, 4 goes to 8, 8 goes to 9, 9 goes back to 1. You could convert that into an array if you wanted to. You could even write it as ordered pairs if you wanted to. But now what I want us to do is write as a composition of transpositions. So the good news is you can actually just do each of these separately and then compose them. What you can do is like write pi, put a bracket. Now, using the same pattern that I used right here, take 1 comma 9 composed with 1 comma 8 composed with 1 comma 4. This composition here of 3 transpositions creates this cycle right here and leaves everything else alone. Y'all see the pattern? So if I said, let's do the next one, how would you write this cycle as a composition of transpositions? 3, 7 composed with 3, 10. And then compose, what about this one right here? But 11, 11 doesn't switch anything, right? 11, 11 is not a switching of 2 elements. So actually you just don't even have to put that in there. Because 11 stays itself. That's not a transposition, just leave 11 alone. And then do the last one, which is 2, 6 composed with 2, 5. Or you could do this completely without the brackets, and it means the same thing. 1 comma 9 composed with 1 comma 8 composed with 1 comma 4 composed with 3 comma 7 composed with 3 comma 10 composed with 2 comma 6 composed with 2 comma 5. And if you don't have 11 there, it's just like when we were doing like 3 on this map right here. If it's not there, it just stays the same, right? So 11 would map to 11 by all of these, right? If you go from right to left and you say, where does 11 go? All the way through, 1, 2, 3, 4, 5, 6, 7. On all 7 of those, 11 just goes to 11, right? So you don't even have to put it in there. Because if it's not there, it's understood. Just like this notation right here. Right? If you write it like this, you're saying 1 goes to 1, 2 goes to 2, 3 goes to 3, 4 goes to 4. So if there's no 11 there, there's no 4 there, there's no 8 there, that means they just go to themselves. Okay. But let's double check. Let's just pick a number. I don't care which one. Pick any number from 1 to 11. 7. Now where should 7 go? It should go to 3, according to this permutation right here. Let's check that if we do it in the composition, that happens. 7 should go to 3, right? So, according to this one, where does 7 go? Stays. And then where does 7 go here? Stays. Here? Stays. Here? Goes to 3. Where does 3 go? here? 3, 3, 3. So 7 goes to 3, check. Just like it's supposed to. You can guarantee that that's always going to work if you use that pattern for creating your compositions. But any permutation can then be created this way. Since we can write any permutation with cycles, then we can do any permutation as a composition of transpositions. How many ways do you just flip elements 2 at a time to get to that permutation? It might help to think of it a slightly different way. You now know how to answer the question in the homework that asks for creating these things. But just think about it this way. Let me go back to the previous example. This is up here. The one that takes 1, 2, 3, 4, and 5 and turns it into 2, 3, 4, 5, and 1. Okay, I said it's this composition right here. 1, 5, 1, 4, 1, 3, 1, 2. One comma 5, composition 1 comma 4, composition 1 comma 3, composition 1 comma 2. So this transposition 1, 2 means take these 2 elements right here and switch them. If you do that, what do you get? 2, 1, 3, 4, 5. Right? And then this one right here says take the first and the third elements of the result and switch those. Now, this is the first and this is the third. Doesn't mean use the actual 1 and 3, but it means whatever you got as a result, flip those guys. So you get a 3 here, a 1 here, a 2 here, a 4, and a 5. Right? Now if I do this right, if I switch now the first and the fourth one, I get 4. Starting to worry that I may be getting this wrong. Let's try it anyways.
1, 2, 3, 5.
According to this, I should. What do I get? Oh, now I'm off. Went the other way. All right, so I screwed something up.
Flip the first and fifth.
I think I did it in backwards order. I think I actually got to flip the first and fifth, and then the first and fourth, and then the first and third. Well, that didn't work, did it?
Good thing.
This should be the same thing if I was talking out of my mouth instead of out of my rear end. All right, something's crazy there. Let's try it again. What if instead of switching, I got a Control-Z button. Watch this.
I've got a severely short eraser.
You guys got erasers? Oh, come on. I'll just erase.
She doesn't have erasers.
All right, so what happens if we switch these?
You get 5, 2, 3, 4.
And what happens if we switch these?
First and 4, 2, 3, 5.
And if we switch these?
3, 2, 4, 1, 2.
And if we switch these?
Check.
Yeah, that makes.
That's what's supposed to happen. Okay, so the reason I did that was not because you're going to have to write this or draw this picture, but I wanted you to realize that you can get to any ordering you want by switching just 2 at a time. I'm claiming I can get from 1, 2, 3, 4, 5 to 2, 3, 4, 5, 1 by flipping 2 at a time. Okay? Every permutation is a sequence of flipping. Okay? Now, interestingly, note decompositions into the composition of transpositions, I've given you one shortcut, but that's not the only way to do it. So what I'm going to say is that this process is not unique. For example, 1, 2, 3, 4 is 1, 4 composed with 1, 3 composed with 1, 2, right? Everyone in here can come up with that one on their own. But it turns out you can also get there by doing swap 1, 2 composed with swap 2, 3 composed with swap 3, 4. I mean, just think about it. This one says 1 goes to 2, 2 stays at 2, 2 stays at 2. So that one works for 1. This one here says 1 stays at 1, 1 stays at 1, 1 goes to 2. If you checked all 4 of those elements, you could verify both of these produce the exact same cycle, and they're completely different compositions of transpositions. Completely different, but result in the same permutation. So that's why I say it's not unique. There's not one and only one way to do it. Again, I've given you the shortcut to get one of them, but you're not necessarily getting the only one. So you might guess by looking at this that all compositions of transpositions for a permutation would be the same size. Does it take 3 for all of them of this size? That is, for this particular cycle, is it always going to be 3? And the answer is no. Here's another one. 1 goes to 2, composed with 1 goes to 4, composed with 2 goes to 3, composed with 1 goes to 4, composed with 3 goes to 4.
Why is 1 goes to 4 and there's twice?
Well, this works and there's 5 of them, but essentially what I've done is I've inserted a transposition where you flip the first and the fourth, and then you flip them back. Right? In fact, I could make these as long as I wanted to by just adding things that flip things back and forth, right? I could have one that was not just 5 but 7 long. I could have one that was 9 long. I could have one that was 11 long by just adding, let's flip these and flip them back, right? Because that would get me the same, it would undo whatever I did to insert that. Okay? So they don't have the same number, but since the only way I can switch two things and switch them back is in pairs, by adding 2, notice that no matter what I do, I'm going to end up with an odd number of them. Okay? Now that's an interesting conclusion. What this actually ends up showing, actually it argues for it, it's not a formal proof, but one of the claims that we can make here is that if you decompose a cycle into these transpositions, then no matter what 2 you come up with, if there's 2 different ways that you can do it, they're going to have the same, what we call parity. They're going to both be odd or both be even. You can't have one that's even and one that's odd. So the number of transpositions that you can decompose a permutation into is always even or always odd. It can't be both. Okay, so let me write that as a theorem. It's kind of a surprising result. Let pi be a permutation of n objects. That's what that statement right there means. And also let pi be decomposed into two compositions of transposition. Which means that pi as a reordering, as a permutation, could be written as tau 1 composed with tau 2 composed with tau. By the way, tau is another Greek letter. Looks like pi, only it has one stem instead of two. Let's say there's n of them. And let's say pi is sigma 1 composed with sigma 2 composed with sigma 3. Sigma is a circle with a line or a stem coming off of it. Composed with, and let's say it's composed with sigma, let's say m. It's a different number of transpositions. Then m and n have the same, I'm going to put this word in here that we haven't really defined, but we'll call it parity, which is oddness or evenness. That's not a word. How many n's do I need in there? Evenness. In other words, i.e., m and n are either both even or both odd. So up here, this 1, 2, 3, 4 was decomposed into 3 different ones, but notice they are all the same parity, right? What is their parity? They're all odd, right? Now there are cycles that have an even number. In fact, we did one. This one right here would be always decomposed into an even number of transpositions. The number of swaps that it takes to produce that permutation is always even. The number of swaps or the number of transposition it takes to produce this permutation is always odd. Because that theorem exists, and I know Kyle's not going to like this, but the proof is omitted. What we can do is define a property of a permutation. A permutation now can be called odd or even. It's not like an odd number, it's like an odd permutation, meaning that the number of decompositions of transpositions that you get is either even or odd. That's how you define it. Let pi be a permutation if any decomposition of pi into a composition of transpositions has an even number of transpositions, then it, meaning pi, is called even. So a permutation is called even if you can decompose it into transpositions and you get an even number of them. If odd, it is called odd. Now there's a lot we can do with this that I'm going to stop and not continue on. There's some interesting results that follow from this new way of categorizing your permutations. But I want you to be able to simply answer the question, if I give you a permutation, can you tell me if it's odd or even? Right? Like if I told you pi is 1, 2, 4, 3, 5. This is the first permutation we looked at in this section. Is that odd or even?
It's odd.
Why is it odd?
Because it has two different compositions.
Because there's two cycles?
Is it because the 1, 2, 4, 3 is 4 numbers, so it's even?
So is it even because this is even? Is it odd because there's a total odd number of objects?
It's odd because
I
that's
think it's
even.
odd because there's an even number.
Okay. In order to create, with our shortcut, a composition of transpositions, you're always going to get one less than there are in that cycle. So what you're saying is correct. That this cycle right here by itself is odd, right? Because how would I write that as a composition of transposition? It's 1, 3 composed with 1, 4 composed with 1, 2. So that's this cycle here as a composition of transpositions. And then this cycle, 5, since it's just 1, there are no transpositions, you just leave it off. So there are 3, which means it's odd. What if I said sigma is 1, 2, 7, 3, 5, 4, 6, 8, and none? Is that even or odd? How are you getting odd?
2 for the first one, 1 for the second, 2 for the third one.
So you can write it out, but actually, once you see the pattern, you don't even have to write it out anymore, right? There's the composition of transpositions for the first cycle. And then the next one is just 3, 5. The next one is 4, 8, 4, 6. And 9 you leave off. So 1, 2, 3, 4, 5. That's odd. This composition of transpositions produces the same permutation as this cycle notation. So y'all see where Randy was able to get the answer without even writing them out, right? This one's going to give you 2, 1, 2. 2 plus 1 plus 2 is an odd number. It's 5. Right? Because you only get 2 transpositions out of this, 1 out of this, 2 out of this, none out of this. So let me give you one more, and you tell me just by looking. If I gave you tau is 8, 9, 7, 2, 1, 3, 6, 5, and a 4. Odd or even? There's 4 here, 2 here. So at least one of the decompositions that I can come up with is 6 total, which means it's even. Which means all the compositions I come up with will be an even number. Could be more or even less than 6, but
I have a question.
yes.
So, the trend seems to be, instead of objects that are in, that each set is the amount of, like, sets. So like, if there's an odd number of sets, it's gonna be even. If there's an even number of sets, it's gonna be odd.
So I had an even number here and got odd. I had an even number here. Okay, so let's
I'm just wondering if that's a
let's test his theory by seeing if we can't come up with another one. Can you come up with one that has an odd number of cycles that is an odd transposition? So let's write 3 of those, and let's make sure it's odd. Okay? So to be odd, you need the sum of these 3 to be an odd number, right? Make sense? So, and what it is the number of decomposition, or number of transpositions is always one less than the number in there. So if you could make all of these even, then there would be an odd number. So if I could do 1, 2, 3, 4, maybe 5, 6, 7, 8, 9, 10, 3, 1, 3 is 7, which is odd. So I came up with one that had an odd number of cycles that was still odd. So that's the exact exercise that mathematicians go through. We look at something, we see a pattern, and then we test it. And if it continues to hold true, then we try to prove that that is in fact true. These are what the kinds of questions that pure mathematicians play with and enjoy exploring.
So it works with odd and odd, does it work with even and even?
But do you think you could create an even number with where they're both odd numbers of elements inside of them? I think we could, right? I could do boom, 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 boom. And so I want it to be even,
1, 2, 3.
which means I need an odd number in here. So 1, 2, 3, 4, 5, 6. I get 2 out of this. I get 2 out of this. So that works.
So what if, I'm gonna keep going on this for just a little bit, because I'm questioning it, because it comes up in an example before too. What if there's one with only one cycle? Like you have on 1, 2, and 3 you have a 1 by itself, a 5 by itself, and a 9 by itself. And then earlier back there's an 11 by itself, and it seems to follow the same trend.
1, 2, 3, 4, 5, 6. I mean, as long as the number of cycles is even, I can just keep adding this. And adding single elements do not change
What if
the
it's
evenness
just
or
a
oddness.
singular element?
Like this.
Yeah.
So what's your question then? There's an odd number of them. Does this have to be odd or does this have to be even?
Yeah, because that one ends up being even.
Right. So what about 1, 2, 3, 4, and a 5 here? There's 2 of them, and it's odd.
Yep.
And if I take this out right here and make it 4, there's 2 of them, and it's even.
It's too
So
small.
you're saying it doesn't depend on that single element?
It doesn't depend on the number of cycles because I can make the cycles larger or smaller as I want. Okay. All right.
It worked for the first 2.
Yes, and I mean, again, that's what you do. There's a formula. Whenever I teach intermediate analysis, it's a good example of this where we're talking. It kind of fits in with when we talk about induction. And I can't remember the formula off the top of my head, but there's a formula that's like n squared plus 3n plus 17 or something like that. That for the first 17 integers that you plug into it, or first 17 natural numbers, always gives you a prime. Like 17 numbers in a row, you plug it in, you get primes. So if you like start with the first one, you start with the second one, third one. By the time you get to like the 15th or 16th, you're beginning to think this formula must be the magic formula that always produces primes. But it's not until you get to the 18th one that you realize, oh, no, it was just lucky. It was a coincidence. There's a lot of problems like that in mathematics where you can try things, what seems like an enormous number of times and always be true. But in mathematics, remember, an example or even 17 examples does not a proof make. It has to be proven true for all of them. So that's why you have techniques like mathematical induction to be able to show not that it's true for the first 17 of them, but that it's true for an infinite number of them. And there's no way to prove an infinite number by testing them all, right? You have to come up with a proof technique that allows you to verify that it's true no matter where you start, no matter where you finish. Okay, that is the end of section 27, and that homework is assigned and due on Tuesday. So here's what I'm going to do. I'm going to stop my recording here. We've got about 15 minutes left in class. Instead of writing this